Hello, everyone. Hope I'm audible. So, my name is Kundan, and I work for Global Open Ecosystem team of Samsung. And today I'll be presenting the topic of rethinking writeback. And Anuj is also there with me, a co-developer. So in today's talk, we'll see about existing buffered I/O stack. And the writeback is the core part of the buffered I/O stack. And currently it is sequential. So we'll see the efforts which we are putting to parallelize the writeback. For the writeback, backing device info is the core structure, and which contains the writeback structure also. We'll go through them. And for parallelizing writeback, we made multiple BDI contexts. We'll see the changes related to that. While we talk about writeback, file system delayed allocation is also a part of writeback. And it is there so that we can minimize the file system fragmentation on the disk. Now with the parallel writeback, we distribute the inodes to various writeback threads. We'll see the various schemes which we have tried and what are the benefits and cons of those schemes. Moving forward, we will also see configurable writeback feature which we have implemented, which helps us to change the number of writeback threads on the fly. After that, we will see the performance gains which happen and which we have measured using various tools. We have used FIO, VectorDB bench, and the kernel compilation benchmarks. So first, going ahead with the existing buffered I/O stack. The buffered I/O stack majorly has 3 threads. First is the application write thread, and then it offloads the work to writeback thread. And from the writeback thread, it offloads the work to kblockd. All these threads are present in kernel. So if we see the application write, application will be writing to any of the file, and that we call as buffered I/O stack. So application, when it writes, the virtual file system write is triggered in the kernel. The virtual file system invokes the file system specific write. See, for ext4 or XFS, we will have file system specific write functions. So now the file system specific write function, what it does, it invokes the IO map functionality. The IO map functionality, depending upon the file system block number, it fetches the extent of the file. And in that extent, we will get the information whether the disk block is already allocated for it or not. If the disk block is not allocated, it is marked for delayed allocation. And the delayed allocation happens at the writeback time, which we'll see in the next thread. So once these things are done, file system tries to locate, or if the page is not there, it will allocate a page or a folio for the corresponding inode. So this page is allocated so that we can copy the data from the user space to this page. And then the inode which was getting written, it is marked as dirty, and it is added to a writeback dirty list. So this dirty list is shared between the write thread and the writeback thread. So once it is added to the dirty list, we wake up the writeback thread. So coming to the writeback thread now, the writeback thread has list of all the inodes present with it. The writeback thread starts taking the inodes one by one from this list, and it starts the writeback. So this part of processing is sequential. After that, the writeback thread fetches limited amount of pages from the inode page cache, and it invokes the file system write page. The file system write page sees for the extent which is present, and it sees that if the extent is marked for delayed allocation, and there might be several extent marks for delayed allocation. So it merges those extent, and it forms a bigger chunk of size, and it does the LB allocation for a bigger chunk. Once the LBA is done and we know where on the disk the data will be placed, we form a bio, and that bio is offloaded to K block D for submission. Here the K block D is already present, per CPU threads are present in that. And from the K block D, the IO submission happens using the block multi-queue infrastructure to the NVMe device or the underlying device. So this is the same flow what I was explaining. The 3 threads are there. Write thread invokes the VFS layer, and then we invoke the file system specific write. We allocate a folio, copy the data from the user. This folio is added to the page cache. Now this page cache is specific to a particular inode. And then we mark the inode as dirty, add the inode to BIO dirty list, and wake up the writeback thread. Writeback thread takes out the inode one by one from the IO dirty list, and it sees for the pages which has to be written, and again calls the file system specific write pages function. The IO map is triggered by the file system specific write pages function, and it tries to merge the adjacent extent and form a bigger chunk of block IO. And yes, the allocation is done by the file system. And then it prepares the bio and submits it to the K block D infrastructure. The block MQ triggers, and then it submits the IO to the NVMe device. So over here, we see that application can issue the IO in multi-threaded fashion, but the writeback is always a single-threaded task. Even the lower K block D layer is multi-threaded. It has per CPU threads present with it. So now this becomes a bottleneck because the writeback thread is only one, and we have multi-threading at the top and at the bottom. So the solution for this is parallelizing writeback. It means that creating multiple writeback threads and distributing the inodes amongst these writeback threads. So this is the parallelism which helps in improving the IOPS, and it is a bottleneck from a long time in Linux kernel. The core of the writeback is the backing device info structure and the BDI writeback structure. The backing device info structure is one per block device, and it has interfaces with memory management and the block IO. So the BDI writeback is the structure which is contained inside the backing device info structure. The various lists of inodes which I was talking about are present in the BDI writeback structure. It also contains flusher thread, dwork, which is the thread which executes the code of the writeback. Also, it has counters for throttling and scheduling the writeback. The various counters it maintains are the page or the folio numbers in form of reclaimable, dirtied, writeback, and written pages. Also, it throttles the IO. There are 2 types of throttling which happens. One is the foreground throttling, and one is the background throttling. So foreground throttling is something like if applications are submitting the IO and they are submitting in a very fast manner, then what will happen is it will try to consume the entire RAM. So once 20% of the RAM is consumed, we pause the submitting threads. This 20% is configurable using the proc file system. So this is the foreground throttling, which happens with the famous balance dirty pages function, or infamous also we can say. The second thing is about background throttling. Even if we are scheduling the writebacks and trying to execute the writeback function, it sees that if we have not crossed 10% of the dirty pages, then the flushing is deferred. The third type of control is write bandwidth control. So the code measures the write bandwidth for a particular device, and it selects only limited number of pages to be flushed to the device. So all this throttling and the counters are maintained in the BDI writeback structure. So the solution or the design what we proposed and which we are working on is initially the BDI has the BDI writeback structure only, and then we introduced multiple BDI writeback contexts. So now every BDI writeback context has its own BDI writeback structure also. So we will have those many dworks present and those many threads we can use to do the flushing of I/O. And also, while doing this kind of implementation, how the inodes are distributed to the BDI writeback. So currently, a better way is we affine the inode to a writeback thread. So if the I/O comes to a particular inode, it always go to the same writeback thread amongst n number of writeback threads. So this avoids the fragmentation, which we'll be discussing in the further slides, how it avoids the fragmentation. Apart from these, we left the throttling code, like the foreground throttling, background throttling, and the other part of code as is, so that we will avoid massive code changes, and it maintains the legacy behavior. So this is complete flow of the parallel writeback, application submitting the dirty pages. And in the file system layer, we select for a particular inode which writeback has to be scheduled. As of now, it is just based on the inode number. When we do a modulo with the number of writeback contexts, and we get the particular writeback context to which we have to schedule the inode to. The inodes are given to the multiple writeback contexts, and as it is given to the multiple writeback contexts, the contexts are also woken up. When it is woken up, it selects the dirty pages and submits the I/O to the storage device. This is done independently of the other threads. So if we are writing to 3 inodes and it happens that they are distributed to 3 writeback contexts, we will have 3 writebacks getting executed at the same time. Going further, I'll discuss about file system delayed allocation. So once the write is issued using the write thread, kernel file system specific write is invoked, and we have extent getting allocated there. This extent sees that if the disk block is not allocated, it is marked for delayed allocation. Delayed allocation means that the real allocation of the disk blocks will happen at the time of write back. So writebacks, in the writeback, we have again file system specific code, and the allocation happens there. So it sees that for a particular inode, the number of extents which are present, and it tries to merge the extents and form a bigger extent. So extent is the file system block number mapping to the disk block number. So that mapping is updated, and since the merging is there at this place, we get a bigger real block allocated, and we get lesser fragmentation. So now we shall not, looking at this diagram, we can say that we shall not distribute the single inode amongst multiple writeback threads. If we do that, we will have parallelism while allocation of the real block, and we will get more fragmentation, and the file system will get fragmented. We'll have more fragments at the disk side. Now we'll discuss about the schemes to distribute the inode to the writeback threads. So initial scheme, what we tried is giving the same inode to multiple write-back threads. What happens because of this is, even if the application is writing to the single inode multiple times, we will have multiple invocations of write-back threads also. This increases the throughput a lot. But the problem with this type of distribution is that the write-back thread will try to allocate the disk blocks in a parallel fashion also. If it does, it will result in the file system fragmentation. So a better approach to avoid the file system fragmentation is to affine the inode to a write-back thread. Now we discussed that inode can be distributed to multiple threads, which will result in fragmentation. And the second way is to avoid the fragmentation. We have to keep the inode affined to a write-back thread. So further moving, even with affining the inode to a particular write-back thread, we see some issue. The issue is of allocation group lock contention. So what can happen is inode 1, 2, and inode n can belong to same allocation group of XFS. And the allocation of block happens from the same allocation group via multiple write-back threads. If that is done, what happens is multiple write-back threads try to acquire the same allocation group lock. And these are semaphores. So multiple write-back threads trying to acquire the same semaphore. If one guy has acquired the semaphore and we have, say, 128 write-back threads, then 127 of the other threads will be waiting on the first semaphore. Instead of increasing the IOPS, in this case, it decreases the IOPS. So allocation group is a basic thing which is present in XFS, and XFS recommends that we have IOs coming to multiple allocation group at the same time. That will give a very good parallelism. So what we did is, instead of affining the inode to a particular write-back thread, we moved ahead and said that, okay, if the inodes belong to same allocation group, we will affine it to only the allocation group. So this way, what we will have is the AG lock contention allocation will not be there. And we will always see increase in the IOPS with increasing number of write-back threads. Now we'll see the configurable write-back feature. So we also added, and this was suggested by Christoph, we also added the ability to change the number of write-back threads on the fly using a sysfs attribute. So user can change the write-back contexts varying from values of 1 to number of CPUs. We have to just give echo the number of write-backs we want to sys class BDI and the block device major minor number and the number of write-backs. How we have implemented this is through freeze and thaw of the file system. So before changing the write-back threads, we freeze the file system, and then again we unfreeze it. So for freezing a file system, first we fetch the file system super block for a backing device info, and then we do a freeze of the file system. It flushes the IOs and also stops the incoming IOs from coming further. Now we iterate through the IOs, flush all the IOs, the pages belonging to those inodes, sorry, not the IOs. So we flush the pages belonging to the various inodes, and then we free the write-back threads. It means that BDI write-back context and the BDI write-back itself, and then we reallocate and register the new write-back threads. After we do that, we unfreeze the file system, and IOs continue after the unfreeze. This helps in getting the base behavior whenever we need, or if some file system want to tune the behavior or change the number of write-back, or some user want to change the number of write-back threads, depending upon their specific IO workload, they can do that as well. So if we change the write-back, it has impact on many other things. It has impact on page migration, memory compaction, and it touches CXL also. And it can help GenAI workloads or the machine learning workloads also. So first thing, we'll discuss about page migration and the compaction. So pages under writeback cannot be migrated. They are marked as unmovable pages in the RAM, and it cannot be moved from one place to another. So what will happen, it will hamper the page migration. So if a lot of IOs are happening, the RAM will look like it has more number of unmovable IOs, and it will be hampering the page migration. And page migration hampering means we will have compaction issues, means we cannot move and compact the RAM and make it less fragmented at a point of time. And it will increase the memory fragmentation also because of these things. So parallel writeback with the CXL ecosystem. With the CXL ecosystem, we get tiered memory approach also, where DRAM is the faster memory and the CXL memory is generally the slower target. But the dirtying of pages happens for both DRAM memory and the CXL memory also. So the flushing of threads, flushing of the pages from DRAM memory or the CXL memory is done in a faster way using the write-back threads. So it enhances the reclaim and the swapping efficiency also. For the Gen AI workloads and the machine learning workloads, what we have seen is Gen AI creates disk IOs in a burst, in form of bursts. So at one time, it will be trying to write many files, and after some time, it will be sleeping. So once it tries to write to many files, parallel writeback helps there by writing all those files parallelly. Like, yeah, different inodes getting assigned to different writeback threads. And we have seen that in cases of checkpointing where the Gen AI is trying to do the checkpointing, it tries to do heavy writes, but it does it sequentially. So if parallel writeback is there, it helps it to write in a parallel way. And the whole entire Gen AI application will not be waiting for the more time. Now we did evaluation with VectorDB. VectorDB is very much required for Gen AI workloads. This database is prepared initially, and it helps in near neighbor search or for similarity. It is designed to scale with growing AI and ML needs, and it uses buffered I/O. So once it generates those files and or the DB, it does it on top of a XFS file system, or on top of a file system it has to do. It can be ext4, XFS, or any other file system. So we did the benchmarking of VectorDB with parallel writeback. We used XFS as the file system for the parallel writeback. And we saw improvement in the real world also because of parallel writeback. We did the evaluation using the FIO benchmarks with inode affine to writeback. And we see very good improvements. And here's the data with varying queue depth and FIO pumping the IO to various files. So here it is 20 FIO jobs and 20 files. And the complete IO is about 600 GB. The next evaluation, what we did was, I was talking about allocation group affine writeback threads. So this evaluation we did, and we see huge improvement in the IOPS because of this. So now here the workload is also tweaked. We write to various files belonging to different allocation groups in parallel. And then we see write-back effects are very good. So here we see about 5 times the IOPS what we are getting, and it is almost saturating the device. The device saturation is about 2,000 megabytes per second, and we are almost reaching there. Otherwise, yeah, in the base case, you see only 365 Mbps is what it was providing earlier without the parallel write-back. The other evaluation what we did in the is with the, it is a real world evaluation which we did with the kernel compilation time. And we see that it reduced by about 10 seconds of the kernel compilation time also. Now kernel compilation time depends upon various factors, the CPUs and other things, and also it tries to write to multiple files at the same point of time. So that small part of writing to multiple files at the same point of time got improved by the parallel writeback. With this, I would like to thank Jan Kara, Christoph Helwig, and Louis Chamberlain, because they have provided very valuable inputs while we designed this solution, and they continue providing their help to us. Also, many other Linux kernel community members are helping us to go ahead with this. With this, I would like to conclude the session. And any questions? Thank you. Yeah.
So thank you for the talk. I'm not an expert in the subsystem, but from experience, other systems might have algorithms to decide which block to write at any given time. For example, least recently used, where you want to select some of the blocks to write first. When you split up to multiple threads, those algorithms now would need to share data or not share data. My question is, are there such mechanisms there, and what is the effect of parallelizing?
So there is, see, these are files, and there is no prioritization between these files. So if we allocate disk block for a particular file, so like a.txt or some movie file or some other file is getting written to the disk. So there is no prioritization as such, like we have to prioritize and something is least recently used or most recently used. So such kind of prioritization is not there. So it is symmetrical. And that's how we just select the number of blocks and then write it to the disk. Yeah.
I have a question regarding debugging errors. When you have parallelization, it's very fast, but figuring out problems with timing and so on is very complicated, or can be very complicated. By file system, I've always been on the safe side, better safe than sorry. And how do you solve these kind of problems?
So, yeah, there are, so if you parallelize, it can happen that there is a single lock present in, because it was not parallelized till now, there can be a single lock present in that thread, which is shared amongst all the threads. So this kind of issue we saw with the allocation group lock. And we test with multiple devices, and we see that always the performance should increase only. If some of the lock is really hindering it, we try to solve it as per that lock. So that's how we are trying to solve it. Any?
This was not exactly my question.
Mm-hmm.
You are increasing complexity. And my question was, how well is the system prepared to handle the increased complexity in the sense to make you a hint what the problem actually is?
So yeah, definitely it is, number of threads are increasing. It will give a amount of load to the system, but there it is also governed by various other related things. Something like write-back throttling is also present. So it will not disturb the system that much. And yeah, after that it comes to running the benchmarks and seeing that is some of the thread is hogging the CPU, or we take the lock stats and see that if some of the lock is getting super used. So these are the things through which we see that how it is performing. And also we have the XFS tests which help us. Like it is series of tests which are run on this kind of change, and then we see that none of those test cases are breaking. So, and we also give our new test cases for Gen AI and ML. We are designing new test cases for checkpointing and other type of workloads, and we see that it works good with all those newer things also. Thanks. Yes.
Question. You showed us evaluation result when using per location group, right?
Yep.
I'm curious about the result when you are using all, when there are many allocation group and when all the allocation group is used. The result.
So you mean to say if all the inodes belong to same allocation group and versus all the files belonging to different allocation group, what is the?
I mean, in a system-wide result, not for allocation group.
In the?
Not for allocation group. System-wide result is what I'm curious about.
Okay, so we do submit, yeah. So if we find the inodes to a per allocation group is what we see. So you want to see the impact on the system wide? So yeah, what I can show you is this thing. If we are submitting IOs to files belonging to different allocation group, we see that parallelizing increases a lot. And if with this kind of a scheme where we are assigning the write-back thread to the allocation group, you write to a same directory again and again, you won't see any improvement in the IOPS because of parallel write-back. But design-wise, it is made like XFS expects. The files from various allocation groups will be written concurrently. That's how the more parallelism will be achieved by the XFS. So that way, we see that if we submit the IOs to various files in different directories, which means that we are submitting IOs to different allocation groups, then we see a very good improvement in the IOPS. So this is about assigning the write-back threads to an allocation group of XFS. Yeah.
Now that you have another parameter that is tunable, the number of threads, which is, before the patch is 1, right, a constant. Now it could be tuned. How do you envision users to interact with this parameter? Do you have a way to automatically set it? Is it dependent on the hardware? Should the hardware set it? So what are your thoughts?
So this tunable parameter can be varied, and in some cases for a hard disk drive, what we saw, so these are the result with the NVMe devices. But in the hard disk drive, because it is a spinning disk and the heads has to be rotated, we don't see improvement with the hard disk drive with the parallel write-back. In fact, we saw about 14% of decrement in the IOPS with the hard disk drives. So for those drives, what we will do is, while the drives enumerate, we will make using the backend device info, we will make the write-back threads as 1 initially only. And this tunable is provided to the users, like if they see such kind of behavior, they can always make it 1 and they will see the base behavior in worst case also. And moving further, we also saw that how it can be tuned. So for XFS, we talked to the XFS maintainers. They told us that vary it not on the basis of number of CPUs, rather you make the write-back threads equal to number of allocation groups. So say for a disk, the allocation groups are 4 and the CPUs are 128. So you make it 4 and then you see how much is the improvement. And if you increase it from 4 to 10 or 50, then you see how much is the improvement. So we see that once it goes to number of allocation group, like if you increase it from 1, 2, 3, and then 4, we see a very good increase in the IOPS. After the number of write-back threads we increase after the allocation group, we see it tapers down. So those are the schemes we can recommend for XFS that keep it equal to the number of allocation groups for XFS. So that way it can help. Yes.
I hope it's a really stupid question. Especially at the low end, is there any risk of hardware vendors cutting corners where devices will no longer work or will not work properly with the extra parallelism that they will have to deal with?
Yeah, so that question, I'll say we tested with multiple devices, and hard disk is one of the things which we saw that it starts degrading the IOPS. So that thing we observed related to the hardware, and other NVMe devices are made for write to any of the LBAs, so it should not create any issue for that. Yes, please.
Have you conducted any tests on ext4?
Yes, we have conducted tests on ext4 also. The improvements were not as great as that of XFS, and we are still analyzing like whether it is because of increased lock contention or some other stuff. Yes, please.
Another question, sorry. So when you have too many threads, now you start having kind of, I guess, interrupts on multiple CPUs to handle those threads. Oh, or context switches, right, like kernel conflict. So it increases overhead. So if you have a very unloaded system, you might have an increase in overhead. Have you observed that, and how much?
Yeah, we see that, okay, now if we submit to, say, if we have made 128 write-back threads and we submit to 60 files, we see that 60 of the write-back threads are getting woken up, and they submit in sort of in a parallel manner. And yeah, because the K block D is also multi-threaded at the bottom, we see that obviously it will be multiple completions because of multiple interrupts. But yeah, I think we are offloading the work to K block D and not seeing much of, again, all the things what we see is IOPS should not decrease, and system should work sanely. So those things are fine, and I think K block D will take care of the interrupts happening at multiple times. Thanks, everybody. Thanks for joining the session.